Okay, briefly what we have here is a buffer. And a buffer is two things. It is a zone of separation between a highly disturbed landscape, disturbed by human beings like in agriculture, and a natural resource. And it's also a functional biological system in which nutrients or pollutants have to go through the system and are filtered or detoxified before they reach our natural resources. So in this particular case we have a research plot in that we've controlled all the variables. You know, we've only got 3 treatments here: grass, alder, and poplar. There's not a mixed buffer, and scientists want to do this so they can control all the variables, try to understand the basic processes, and break it down like that, and also so it will be reproducible. And you'll also notice that we have replicated our plots. You know, we have three sections here: grass, alder, poplar, kind of semi-random. I don't know if you can randomize 3 things, but randomized replicated plots. And so what we've done is to look at how much these buffers reduce the amount of nitrate and phosphate in our groundwater, and how much the nitrate and phosphate in soil solution changes over the seasons. What we found just generally from these plots is that they're highly affected by site heterogeneity. And by that I mean, you can kind of look over here at this alder plot and see that the middle of the stand sort of dips down. Well, there's a big sandy area right there. And this whole drainage area is part of the Woodward Creek drainage. I'm sure that at one point in time in geological history, this was that stream probably meandered down through here, and so there's a very sandy area right there. And those trees performed poorly. On this side, these trees are really doing quite well. This soil over here is a lot richer in organic material. It is a little lower in topology with respect to that side over there. And so that affects things. During our flood stages, the creek will rise up and actually come up about 1/3 of the way into these plots. And the creek will rise about 4 feet. And so during that phase, you know, we've got a lot of nutrients and sediments deposited in those plots. Okay, so site heterogeneity made a big impact on this research. The other thing that made a big research impact is the proximity of the nitrate inputs. So you can see along this grass plot and this alder plot, they're very close to this field that's receiving somewhere between 40 and 60 pounds of plant available nitrogen per year. Those plots down there, you know, the closest nitrate is maybe, our nitrate application source point is maybe 150 feet away. So that made a big impact on how these buffers function. So when you look at, on this graph, nitrate influx going into the buffer, you can see in this alder plot down there, our nitrates are increasing over time. And same with this grass plot right in here, whereas down over there, we see actually sort of a decrease in nitrates over time. So one of the things we do is measure the overall efficiency of the buffer in reducing groundwater nitrates by calculating, or essentially subtracting what's at the bottom from what's at the top and turning it into a % difference. And what we found was that even though this grass plot is getting higher nitrates over the year, it's attenuating or reducing the nitrate levels quite a bit by the time it gets to the bottom of the plot. So here, this is a collection of graphs showing the nitrate concentration at each one of these well sampling points down through the buffer through time. So this is at establishment, and then here's at the end of the year at this grass plot here, and this is at the top of the buffer and at the bottom of the buffer. And so you can see that we're getting pretty good attenuation, and when you calculate the efficiency, it's up above 99%, even though the influx is quite a bit, you know, pretty high. Down at that end of the plot, the influx is low, and you look at the grass at the nitrate levels through that grass plot, it's pretty much near background levels. So I think if we had to do it over again, we would probably plow in a strip here and apply even nitrates across the whole treatments and see what the attenuation would be.
What depth of groundwater are you sampling?
Okay, good question. Generally, I mean, through the whole plot, they range from about, if you look at penetration into groundwater, it ranges from about 2.4 to 4.5 feet. So these wells will penetrate between 2 and 4 feet of the shallow groundwater. Okay.
And you're definitely capturing the top layer?
Yeah, so we're not really seeing, we didn't really examine mixing or look at deeper, possibly upwelling sources of groundwater.
There could be some dilution there.
Exactly. Right. That's a whole, yeah.
So does nitrogen fixing of the alders play a role in this at all?
That was another question that we addressed. The question was, does nitrogen fixation by the root symbiont Frankia that is associated with alder, does that contribute to the groundwater nitrates? And that's one of the reasons why we were establishing that, because it is thought that alders would actually increase groundwater nitrates because of this association with Frankia, and possibly through root turnover increase more shed nitrates into the groundwater. And what we found was inconclusive evidence, primarily because this plot here is so heavily influenced by that field and the performance was so poor. Down on this plot here, where the performance is good, we see that we don't see an increase in nitrates over a 2-year period. So we're thinking, well, this plot here says, no, that's not a big concern. Okay. Another thing to take away from this is that there's a seasonality to the amount of nitrates going through the system. If you kind of take a 30,000 foot look at these plots, you'll see that you get big peaks in the wintertime, here, where the precipitation levels are really high. So groundwater nitrates are increasing at periods of time when the precipitation is high. In the summertime, we kind of get a concentrating effect. So in the summertime, you see low levels in the groundwater, but if you look in the soil solution, they peak up, mostly because of evapotranspiration is actually concentrating nitrates. And then in the wintertime, it flushes down. So there's this pulsation of effect of groundwater going into the streams through the seasons. I just want to talk real briefly about critical factors for buffers. What we're looking for in buffers functionally is to increase opportunities for groundwater to stick around a while. If you have highly porous soil or steep banked buffers, or a steep bank, let's say, then you have this situation where groundwater doesn't stay around very long. And so that means there's little opportunity for plants to extract and assimilate the nitrates. And it also, there's not enough opportunity for soil microbes to break it down through immobilization or denitrification. So increasing the residence time is critical. The amount of soil carbon is highly critical for these microbial functions to happen. You know, denitrifiers have to have carbon in the form of root turnover, exudates from roots, leaf litter that decomposes. All these sources of carbon are food for microbes that use that carbon and nitrates together to denitrify these pollutants. And finally, another important function is shading. So buffers, in terms of providing a function for the stream, it is to provide some shade and some temperature regulation for these waters. Salmon require lower temperatures so that the oxygen concentration can stay high, and shading is a real critical function. So if you plant trees that can provide shade, that's good.